probes. If you have questions, just click the action below. Bert, please unmute.
Yes, excuse me, thank you. It's very interesting and a lot of very interesting mathematical concepts there. I'm afraid I'm very weak on the connection to the black hole. I wonder if you could explain a little bit more exactly what this ring down would mean. I mean, what are you? I understand how the ring down that you get in a black hole because when they collide, because they're actually radiating energy. But what happens? What is it that you're trying to look at here? You have just a single. I understand you have a potential which is of the form of a saddle point, and now are you giving somehow creating a wave packet of an incoming particle, a single, just a single, it could be an electron, I guess. It doesn't have to be, it could be at nu equals 1, coming along one of these, an equipotential line. And then if it's just somewhat below the saddle point energy, then it's mostly reflected, but a small amount is transmitted. And now, are you looking for some time-dependent oscillations in what's transmitted or in what's reflected, or is it just spatial dependence beating? Could you explain a little bit about that?
Yes, thank you, Bert. That's a really good question, and more or less you answered a significant part of it. I should say, let me just say one comment on the black hole. So the black hole, even if you take a single black hole, these are sort of characteristic modes. So for example, if you looked at it's very interesting. If you looked at the scattering matrix, you can just have a scattering matrix formalism. And if you look at the poles, actually, I just want to say that even with a single black hole, it turns out that if you look at the poles of the scattering matrix, and actually this thing here on the right bottom, I think it'll more precisely answer some of your questions. So if you look at the scattering matrix, you actually find that there are these imaginary energy solutions, and these are these quasi-normal modes, and they refer to this characteristic decay. It can happen even in a single black hole, and the reason that you can't probe it in black holes is that you just don't have anything massive enough to perturb it. And this is why you have these two collisions, and it's kind of like the ringing of two bells that are colliding, as an analogy. In the quantum Hall system, though, we do have, it's exactly as you said, we do have probes, namely any kind of wave packets. And as you said, the simplest case would be electrons. And so you can exactly think of that where you have a pinched geometry. And if you had a very, very dilute beam, our prediction is that exactly as you said, wonderful. Thank you for bringing in all these really great points. What you would see is when you see the scattering off, we are predicting characteristic times for when you see this sort of decaying oscillation. We're predicting that there would be these oscillations. And what you could do is you could sit somewhere far away from the saddle. So put a lead somewhere a little far away. And so we have both the spatial, of course, we haven't considered edge state physics, so one has to be a little careful, but I do believe that even in spite, this will go through once you consider the edge as well. And you should be able to, sitting at some position and observing as a function of time, you should be able to see this oscillatory behavior.
Thank you.
Thank you.
Janatra, I saw you raise the hand before. Did you still have a question?
If Jinendra doesn't have a question, I have a comment for him. Did he ask a question? Did he ask a question?
No.
Okay.
Yeah, please.
Okay, so let me just say that he and Steve Kivelson have this really nice work that I really love. And I think, I can't remember the reference, but I think that's one piece of work that actually considers this kind of, I believe it's a WKB type of thing where you can actually consider what the tunneling is between one edge and the other, and it's done through the bulk. And so that was for a single particle. And when I say I'd love to look at extensions for these two anion processes, that's kind of really the reasoning that I'm thinking of. So can we actually, the way that they did it for a single particle, can we actually do this for two particles? So that was just a comment.
Yeah, Dima, do you have a question?
Yeah, so it's a very interesting analogy with black hole physics. I wonder how far it extends. For example, do you have any analog of the information paradox?
So I think we should think about this, Dima. So in fact, we can talk offline. Yes, I do. I do actually. And by the way, we have two papers out on this recently. There's a short paper summarizing what I said. There's a much longer paper that talks about the parallels and entanglement and things like that. And by the way, I should also mention some of the previous work that's looking at this, you know, the point is you're looking at sort of tensors, right? This second rank tensor. And I think I should just mention that the reason that I think the quantum Hall system is so great is that, like gravity, it actually gives a potential for looking at these rank two, you know, and in this case, it could be the saddle point, but it's really the stress and strain and all that. So one point that I want to make is that the parallel with things like gravitational waves is so beautiful because you have these higher rank tensors naturally to play with. Point one. Point two, with your question on information and things, actually this inverted harmonic oscillator has a very rich connection. And now, this is sort of not things that I know too well yet, but quantum gravity and the like. There's a lot to do with sort of information and things like that. So let me just comment that even if we were to take up classical things, and I would say the Hawking radiation, if you look at the original paper, it's really, really beautiful, where you're really looking at quantum fields and saying, in this accelerated frame near the event horizon, how does thermality look like? So it's a beautiful, simple application of, I would say, quantum in the presence of gravity. So now I believe, and I'd be really delighted to talk to you more, if you look at things like entanglement and the like, one can start probing further and asking what the parallels are. Another thing that people have looked at with these, now with edges, is things like quench dynamics, and you can see how entanglement spreads and the like. And it's very doable because you have this point contact and you just turn it on, right? I mean, I don't know, the experimentalists can tell me, but relatively speaking, it's something easy to do, I think. So to answer your question, I do believe there are some really nice parallels to the information paradox, and maybe that's something specific to target.
Thank you.
Okay. Thank you for the question.
Yeah, we saw Janeja come back. Janeja, please unmute.
Hi. So I have kind of a conceptual question, maybe just my lack of understanding, but this is about the interference experiments.
Okay.
So, and maybe it's anybody can answer it, you know, I would. The question is, in these experiments from Mike Manfra's group, what exactly is being, what is the statistics that's actually being measured? So, I mean, the way I look at the problem, there are three different types of objects. One is composite fermion in the ground state. And composite fermions, they actually are carrying flux quanta, so they have their own braiding statistics. It's integral statistics, and that's what gives rise to effective magnetic field. Then we have excited composite fermions, which are quasi-particles, and we have holes within composite fermion lambda levels, which are quasi-holes. Now, these objects have relative braiding statistics also. So the question is, how do, so the relative braiding statistics of a composite fermion in the ground state with respect to an excited composite fermion is actually the same as the relative braiding statistics of two quasi-particles. So the question is, should I think of a fractionally charged quasi-particle going around the edge? Is that a well-defined concept, given that there is no gap at the edge? Or can I think of a composite fermion going around the edge and giving rise to this fractional statistic? So what is the picture that I should carry in my mind?
Jainendra, I think you open this up to anybody, correct?
Yeah, it's open to everybody.
So, and especially given, I mean, I'm happy to speculate, but especially given that it was for the experimentalists, I think my role is to just put this up. I don't know, James or anybody else who's analyzed this more closely. Do you want to say a few words?
Well, my possibly naive picture of this has been as these fractionally charged quasiparticles traveling along the edge. But perhaps there's a more deep interpretation that someone who's thought more deeply about this theoretically could provide, so that you are measuring the statistics of the fractionally charged quasiparticles, but perhaps someone else can chime in.
It looks like there's some raised hands.
Bert has a comment on this.
Okay, so I would say that this is a very good question. There are subtleties that are often swept under the rug here, and so certainly what is looking at with these glitches is you're adding or subtracting a quasi-particle in the bulk. And I think that's well defined. We know what that is.
Well defined. Correct.
But now what the claim is that you're looking at an interference that you can talk about it as you can understand it as an interference phase that's picked up by a quasi-particle of, let's say it's in this case, a 1/3 charged quasi-particle moving around the edge. But of course, you're right that it's not, if you look at the edge, it's really much more complicated than that, because you have, it's gapless. There are, in some sense, an infinite or large number. There's a sea of quasi-particles, and you're doing an experiment in which you're running a current through. So you're adding one additional quasi-particle above this C, and if these were, you could think about them as adding, in the case of nu equals a third, where it's relatively simple, and there's only one mode, then you're adding you're adding an extra bump on this mode, or so, and it travels around, or it's an extra quasi-particle, and the fact that it behaves exactly the same way as you would naively expect for just a free quasi-particle, it picks up the same phase. It's not 100% obvious, but you can justify it in many ways as long as it's just a simple edge and there's no edge reconstruction. And if you have a sharp edge, like you would have in an ideal Laughlin state that just terminated, then you can sort of show it rigorously, because you can actually see what the wave functions look like. But But once you have things like a soft edge and edge reconstruction and so forth, there's quite a bit of argument that needs to be gone through to say that, well, you really have just a single mode going around. And if you look at what's really going on, you're going to have a one propagating mode that goes around the edge that's embedded in a region of localized, there's always going to be disorder and localized, you'll have localized quasi-particles inside localized quasi-holes just inside this edge state and localized quasi-electron just outside the edge state. And you have to go through a bit of hand-waving argument to really make it clear that none of this, that it still has just a single, there's just a single state that propagates around, and there's a single phase associated with this state, and that is what you're measuring. And it's not rigorous as far as I can see. We looked at it when we did this work with Nader and Stern and Rosenau. When we looked at just what happened, even in the integer case, it's still, you still have to worry about what exactly is going on at these edge states, and we sort of convinced ourselves what was going on. And that's what everyone assumes, and certainly it's what happens if there's a really sharp edge. But there is certainly something that's not trivial here, and that's why these experiments are exciting in some sense, because it's not a rigorous. I think it's rigorous that if you had two quasi-particles in the bulk at nu equals a third, they would have they really cannot escape the fact that then they would pick up they would have a phase of 2 pi over 3, whatever. But that it actually also applies to an interference experiment at the edge is really, there's a lot of subtle physics that has to be just right. I mean, I think it's right, but there is subtleties. So I think it's a very good question.
Yeah, I think since here is in the Q&A session, I would suggest if you have a question, you can just unmute and ask.
Hey, Bert, this is Mike.
Yes.
But that sort of begs an interesting question. We've done this at 1/3 where it's easiest, and you have the simple mode structure you believe, and it seems to, the results seem to comport with this picture you just presented. But now we're moving to more complicated states and with more complicated edge structure. So from what you're saying, does this have to be evaluated on a case-by-case, you know, the sort of the validity of the simple picture we're using? Does it have to be validated on a fraction by fraction basis, or what? I'm not sure exactly what the implication is.
Yes, well, we believe in the integer case, at least we believe that it basically still works. So now you don't have any on phases, but we still have to ask what is it, what do you see in an experiment? And then if you have multiple edge modes, each one can be picking up a different phase, and then you have to ask, you know, if there's, say, 2 edge modes, are you going to see interference from just one edge mode or 2 edge modes, or particles scattering back and forth, especially if you have impurities scattering between the edge modes? Exactly what happens. And of course, if you have many edge modes, you're going to get, you may tend to easily wash out the, you might easily wash out the interference signal if you have many competing interference modes. And whether that is a problem, particularly when impurities are present, in the case of multiple modes, in let's say at 2/5, if you're looking at 2/5 or 3/7 or something, I don't think it's been studied properly. So I would say and of course, you know, it's been very hard to see, as you know, the braiding statistics or in fractions, and that may be part of the reason. There's short coherence lengths. I don't know, but the question of whether it would persist, I can't say. The analysis that's been done up until now is been based on assuming that you have sort of ideal parallel modes. In the case of nu equals 2/5 or something like that, or nu equal, you have edge states that propagate reasonably well around the around your interference region without getting too badly mixed with everything else that's around there. So this needs to be, it deserves further work.
Okay, thanks.
So
And if you could do experiments, that'd be fantastic.
Well, we're trying.
So I would perhaps add a little bit to this comment, because I would tell that in response to Jane's questions, that there are actually two questions in one, and one is somewhat easier, the other is somewhat harder. The phase accumulated in this experiment is actually two phases. One is statistical, the other is Aharonov bomb. And one may argue that the statistical phase is somewhat tamer, for the reason that if you have some quasi-particles deeply in the bulk, you know what phase is associated with them, and then you have a lot of gauge freedom in thinking how you accumulate it. You don't have to think that you accumulate it gradually on a circle. You can choose a gauge where you accumulate it strictly inside the tunneling contact. And what happens in the tunneling contact, we understand pretty well. A quasi-particle forms and actually travels through that contact, and then the statistical phase is presumably well-defined and quantized, but there is an Aharonov bomb phase, and the same trick would not work for it, because you really need to understand what exactly the trajectory along the edge is. And that's extremely painful question, because if you try to think of that microscopically, you discover that there is not one trajectory by many. And so this experiment is well defined, only it happens that all of these trajectories produce different phases, but they differ by multiples of 2 pi. So it's a very subtle thing. There is no really single phase. There is only well-defined e to the power of phase. And I think it's much easier to justify that it is just a single number for the statistical phase than for the Aharonov bomb phase.
Okay, so are you saying that the statistical phase is accumulated only during the
Inside the tunneling contact, you can choose a gauge like that, but you cannot play the same trick with the Aharonov bomb phase. And as Bert mentioned many times, you actually have an issue even at nu equal to 1 when the statistical phase doesn't exist. But the Aharonov bomb phase doesn't disappear, and that's a painful part of the story. Because definitely there are multiple Aharonov bomb phases. Definitely it's not just one trajectory, but it looks like they all differ by a multiple of 2 pi.
I see.
Thank you for this very insightful discussion. Andrew, do you have anything to say about today?
Today was great. So tomorrow is the last day. Thanks everyone for coming and for giving talks and participating in the discussion.
Bye.